Wind Power students, Dr. John Troggy here, and welcome to the first lecture of the semester. We're going to be taking the textbook more or less in order over the course of the semester. We are going to be adding things to the textbook because I think there's a lot of interesting topics about the low-level winds and so on associated with wind power that the book either just sort of glosses over or just completely omits. But we're going to start today with the first chapter, and, well, to be honest, an awful lot of what's in the first chapter is pretty basic stuff. A very brief overview of like the structure of the textbook and so on. None of that is exactly going to set the world on fire. But then the author poses a set of questions that I think we should talk about. In his exercise 1.1, he says, suppose that you have a 1 meter by 1 meter frame facing directly into the wind. I think actually in his description he said it was a soccer goal. But whatever, I mean, you can kind of picture here. We're talking like a 1 meter by 1 meter square frame, so it has 1 square meter of area. It says if the wind is moving at 10 meters per second and the frame is directly into the wind, how many cubic meters of air is passing through that frame every second? So here I have my little frame here. I'm trying to show with a little perspective here. And I'm saying, hey, what if there's a 10 meter per second wind pushing through that frame? Hey, 10 meter per second. I see that I have m for meter and I have a second to the minus 1. We're going to be using negative exponents like that in this class. Now, undoubtedly at many points in your education you've learned about negative exponents. I'm not going to teach you I don't plan on teaching you how to work with exponents in this class. I'm assuming you know it. I'll put some links for more information about working with negative exponents in case that's something that you're not comfortable with. And of course, let me know if you have problems with that. We'll work on it, okay? But for now, remember, like, if it's got a negative sign, it means it's like in the bottom. It's in the denominator of a fraction. So s to the negative 1 means meters per second. So here's my 10 meter per second wind headed right into that 1 square meter area. And so I'm kind of using this box to illustrate that's the air that slid through that 1 square meter area in a 10-second period. And of course it has a unit of 10 cubic meters. Because that would be how much, it's not very well drawn to like scale very well here, but so it would be a 10 cubic meter volume of air that slipped through that 1 square meter cross-section that was facing into the wind. That's not exactly so exciting. On the other hand, we're going to build on that here. It says, exercise 1.2, suppose that the density of the air was rho kilograms per cubic meter. Real quick here. That little Greek letter there you're seeing, that's a lowercase rho. Okay, it kind of looks like a P, maybe even a little bit like an italics P or something like that. But no, it's a rho. And notice that the units of density are kilograms per cubic meter. Again, notice the negative exponent there. So it's how many kilograms of, in this case, air there is per cubic meter, box of air. How many kilograms of air are going to pass through that frame in a second? Okay, well, we have 10 cubic meters of air passing through, and a basic idea from physics here would be that mass is equal to volume times density. See, we can cancel out, I have the units over there in the bottom right corner of the screen. Notice how that means that the units on the left-hand side of the equation are kilograms. That means the units on the right-hand side have to work out to kilograms. Well, it's cubic meters times kilograms times meters to the negative 3. So when you multiply that out, remember when you multiply, you add exponents, you get rid of the meters, right? And so this all works out. All right, so if the mass of the air that's passing through is just the volume times the density, and the density is just rho, well, we knew the volume was 10 cubic meters, so our mass of air that is passing through that frame is 10 rho kilograms. Okay? Now, just to give you a sense, by the way, a typical value of rho near the Earth's surface is about 1.225 kilograms per cubic meter, and density, of course, always decreases as you go up in the Earth's atmosphere. Question 1.3. Now suppose you have that the speed of the wind was actually something different than 10 meters per second. In fact, let's make it pretty general and say u meters per second. Okay, u is one of the ways that meteorologists tend to write part of the wind speed. So we're just using their symbols here. U meters per second. Hey, let me just draw your attention to something. Typically, when you are typing up equations and symbols and stuff like that, variables get written in italics, units get written in not italics. So notice how I've got like U meters per second written there, okay? I'm going to try to be very consistent about that in PowerPoint. I'll be honest, I'll undoubtedly make many mistakes, but we're going to try anyway. We're going to strive so that we can keep straight which ones are the units and which ones are the variables that we're working with. So if the wind is U meters per second, how many kilograms of air are going to be passing through that frame every second? So see how I changed the arrow there with showing the wind? I changed it from 10 meters per second to now just U meters per second. So the volume slipping through that frame every second is now U cubic meters. Well, again, if mass is equal to volume times density, mass equals volume times rho, well then if the volume was just U cubic meters, then mass is just U times rho. So we could actually make that box there show that it has U times rho kilograms of air passing through it every second. Now the fourth question that he poses is not really something we can like draw a picture here and do. He just asks, what is the definition of kinetic energy? Kinetic energy, of course, is a property of things that are in motion. It's what our windmills and turbines and stuff like that are going to be trying to capture from the air to convert into some kind of useful form of energy. We're going to use the symbol E kin for kinetic energy in this class. We're going to try anyway to be consistent about all these kinds of things. Notice again I tried to make sure that was in italics and so on. And again, if you're a survivor of like high school physics or general physics at Creighton or something like that, you know that in general the definition of kinetic energy is 1/2 m times, well, usually in physics I'll have used the symbol v for the speed of the object in motion. We're using u here, so it's 1/2 mu squared. Okay, so that's just our definition of kinetic energy. Kinetic energy has units of joules, you probably knew that already, and so on. But this leads us to a fifth question then. How much kinetic energy is passing through that 1 square meter frame every second? See how we're headed towards what a wind turbine is going to be doing? We're going to be talking about the energy that it captures from the wind. Now, we're going to say then that we have a wind of speed of U meters per second and a density of rho and so on. So we know that the number of kilograms of air passing through that frame, that 1 square meter frame, every second is U times rho kilograms. All right, that's the mass. So if I take my little definition there that I had of kinetic energy of 1/2 mu squared, and I take that mass out and I replace it with U times rho, because that is what the mass passing through that box every second is, hey, I can do a little arranging there and see that it's actually 1/2 rho times U cubed. It's proportional to the cube of the wind speed. That's really interesting. Kinetic energy is proportional to the speed of the wind, but when you work with it in terms of the density of the wind, then you actually have it in terms of the flux, to use the right word. The flux of kinetic energy is proportional to the cube of the wind. That's amazing. That means every time we double the speed of the wind, we're increasing the amount of kinetic energy passing through the area of a wind turbine or something like that by a factor of 8. Wow. Stronger winds are going to make a huge difference. That's going to have a lot to do with, of course, how we're going to decide where to put wind turbines and so on. Notice again, just to highlight it here, my units of kinetic energy are going to be joules. Units of energy are always best expressed in terms of joules. So this is how many joules are going to be of kinetic energy are going to be passing through 1 square meter per second. That is what we call in science a flux. That is a flux of, in this case, kinetic energy through that area. The units being joules of energy per square meter per second. In fact, this idea of a flux is a very powerful thing. That's actually why we're working through all this, is to learn about flux. Flux is an idea in science. Flux is stuff, in this case kinetic energy, passing through a square, through a unit area per unit time. Flux is stuff per square meter per unit time. And it's a very useful concept all over the place in science. Let me pick two that would be kind of related to meteorology and power and so on. How about rain rate? Okay, I've got the rain falling here and I have like a unit area drawn kind of in perspective here on my puddle that it's forming here. A rain rate is a flux of, in this case, water. It is the rate at which how many kilograms of water are falling on a square meter every second. So the correct SI units for a rain rate would be kilograms per square meter per second. Now that's hard to see how exactly, I can picture, okay, here's a square meter, so many kilograms of water, it's probably a very small number of kilograms, are falling on that square meter every second. We can actually get this though into a more familiar looking units by dividing through by the density of water. So if you divide through by density of water, which has units of kilograms per cubic meter, you can do the math and see that that's going to work out to having units of meters per second, which might not seem like a rain rate, but keep in mind that we can do the math and change that meters to, we can convert it to like inches, and we can do the math to convert that per second to like per hour, and we can get like inches per hour. Well, that does sound like a rain rate. A big heavy storm might have a rain rate of 1 inch per hour or something like that. Oh, okay, so it's a flux of liquid water. Or we could talk, for example, about a flux of solar energy on like a solar panel or something like that. Here we could talk about solar energy in terms of joules that are incident upon a square meter of a solar panel per second. How many joules of energy per second are landing on 1 square meter? Again, we'd have units of joules per square meter per second. It looks like a flux to me. By the way, I know that this idea of like joules often is not the way energy people want to talk about, energy. A joule per second has units of watts. Watts are power. Power is always energy per unit time. So a lot of times we talk about like kilowatt hours. Okay, a kilowatt hour, they just multiply through by hours again. So a joule per square meter per second, for example, you could rearrange and take that joule per second and turn it into watts. That's a unit of watts per square meter, a very common unit for something like the flux of solar radiation on a panel. So anytime you are transporting something through an area per unit time at some speed or something like that, that's a flux. Alright, so in this case here, we're talking about the flux of kinetic energy through an area swept out by the blades of a wind turbine or a windmill or whatever. So here's a windmill, it has a radius of some number of meters, r, and notice I made a mistake here, I should have made that r in italics, whatever. We're going to try to be careful about such things. So over this area, pi r squared, there is some, that is the area in which it's potentially capturing kinetic energy. And so, if the wind speed was u meters per second, we know that there is a flux of kinetic energy through each square meter of 1/2 rho u cubed. That's our flux. It's got units of joules per square meter per second. So we have that much per square meter, and we know how many square meters there were through that cross-section of the windmill. And you could actually work through to find out how much kinetic energy is passing through the area of the wind turbine and you just multiply out the area times the flux, and you get, in this case, it's pi over 2 r squared rho u cubed. Okay, just a little bit of algebra there. That's how much kinetic energy is passing through the area that's swept out by the blades. Doesn't mean that the windmill can actually convert that into useful energy. In fact, there is a limit as to how much energy can be captured or harvested from the wind, based on the wind speed and so on, and it's actually called Betz's law. Now, Betz's law is actually going to be the topic of the next big lecture in the class, but just to give you a hint ahead of time, it works out to 16/27. No matter what the wind speed is, and no matter how much kinetic energy the air has, the best a windmill can do is harvest 16/27 of that energy, capture it, and make it, convert it into electricity or whatever. 16/27 works out to really close to 60%. It's 59.5 or something like that. Now, in the next lecture, we're going to find out why that is, why there is this limit, and why it's that weird number, but for now, that's good enough. Now, before we move forward, what I like to do in these online lectures is sort of pose some questions for you, and what you're going to do is we're going to go over the question here, and then you're going to choose from the links below here. You'll see that there are, these 4 options in this case, and based on whatever answer you give, you'll get some feedback, and then there'll be a link to move on to question 2 and 3 and 4 and so on as we go through this. Just so we're clear, I have no way of finding out what you did here. Okay, you're not being graded on this. The computer's not keeping track of, oh, this student answered this many of them right. No, these are purely for your benefit to make sure you understood. I'll also tell you that I'm kind of a lazy guy, and a lot of these questions or something similar to this are in the pool of questions that we'll be asking on quizzes and so on. So, it's kind of to your benefit to make sure you know how to actually answer these questions. Alright, so here's question 1. Which of the following is a unit of kinetic energy? Watt, joule, joule per square meter, or watt per square meter? Which of those is a unit of kinetic energy? All right, make a choice from one of those 4 options and get a little feedback before you move on to question 2.